In the last class, we defined mutual information. Mutual information is equal to average number of minutes necessary to specify an input signal before receiving an output signal less the average number of minutes necessary to specify an input signal after receiving an output symbol. This definition of mutual information can also be interpreted as the average uncertainty of an input signal before receiving an output signal less the average uncertainty of an input signal after receiving an output symbol. This in turn could be interpreted as the uncertainty resolved or information received. In the last class, we also took an example of a binary symmetric channel and we calculated the mutual information for this binary symmetric channel. The expression which we had derived is given as shown here. We showed that the mutual information IAB is equal to entropy function where the argument is WP plus W bar P bar minus the entropy function where the argument is P. Now, let us try to provide a geometric interpretation of this result. Entropy function is depicted by this curve shown here. So, if we choose some value of P where P is probability of error on the binary symmetric channel, then corresponding to this P I have a P bar which is indicated here. Corresponding to this P we have HP as shown on the y axis here. Now, omega P plus omega bar P bar is a point which lies between P and P bar, because omega is the probability of occurrence of input symbol 0 which lies between 0 and 1. So, the point indicated by WP plus W bar P bar is a linear interpolated point between P and P bar. Therefore, from this figure it implies that H of WP plus W bar P bar will be always greater than HP. So, what it implies that this quantity will be always non-negative. So, this is a geometric proof of the non-negativity of mutual information. We had proved in the last class that the mutual information is always non-negative. So, if you look on this figure, the difference between these two values is the mutual information. Now, certain limiting conditions of interest may also be seen from this figure. For example, for a fixed value of P, we may vary omega and examine the behavior of IAB. We see that IAB achieves its maximum when omega is equal to half and the value of this maximum will be equal to 1. In this case, the mutual information will be 1 minus HP. This will be the value of mutual information. For omega equal to 0 or 1, on the other hand, the mutual information is 0. Now, after having looked at a definition of mutual information, let us look at some of the information channels. We define two special types of channels and obtain simplified expressions for the mutual informations of these channels. Now, in our discussion that follows, we will assume that each column of the channel matrix, that is P, has at least one non-zero element. So, what this means that an output symbol corresponding to a column of zeros will occur with probability 0 for any distribution over the input symbols. it is therefore of no interest and may be ignored. So, let us first define a channel which is called as a noiseless channel. A channel described by a channel matrix P with one and only one non-zero element in each column will be called a noiseless channel. An example of the channel matrix of a noiseless channel is given as P is equal to So, each column of this matrix has only one and only one non-zero elements. Now, the channel diagram for this noiseless channel is indicated as shown here. The size of the channel matrix is 3 by 6. So, we have 3 inputs. Let us denote those inputs at A1, A2 and A3, and we have 6 outputs indicated by B1, B2, B3, B4, B5 and finally B6. So, probability of B1 given A1 is half, probability of B2 given A1 is also half, probability of B3 given A2 is 3 by 5, probability of B4 given A2 is 3 by 10 and probability of B5 given A2 is 1 by 10 and finally, the probability of B6 given A3 is equal to 1. Now, a binary symmetric channel is of the with the channel diagram is as shown here. So, a binary symmetric channel with a probability of error that is equal to P equal to 0 is an example of a noiseless channel. Note however, that a binary symmetric channel with probability of error equal to 1 is also a noiseless channel. So, what it means that a channel which is consistently in error can be as useful as the channel which is consistently correct. So, after having defined a noiseless channel, let us look at a definition of another specific channel, and that definition for that is as follows. A channel described by a channel matrix, that is capital P, with 1 and only one non-zero element in each row will be called a deterministic channel. An example of a channel matrix for a deterministic channel will be as indicated here. Now, since in this channel matrix there is only one non-zero element in each row, and since the sum of the elements in each row must be 1 for a channel matrix, what it implies, the elements of a deterministic channel matrix are all either 0 or 1. The channel diagram for a deterministic channel will look as follows. Since the channel matrix size is 6 by 3, what it implies that we have 6 inputs which are indicated by A1, A2, A3, A4, A5, A6, and we have 3 outputs indicated by B1, B2 and B3. Probability of B1 given A1 is 1, probability of B1 given A2 is also 1, probability of B2 given A3 is 1, probability of B2 given A4 is 1, this is also 1, and finally probability of B3 given A6 is equal to 1. So, this is a channel diagram for a deterministic channel. Now, let us carry out the calculation of mutual information for these two types of channels which we have just defined. So, let us first consider a noiseless channel. So, for a now, in a noiseless channel, an example of which we saw earlier of this form, when we observe the output B j, we know with probability 1 which A I was transmitted. That is, the conditional probabilities of P A I given B j are all either 0 or 1. So, using this fact, we can write the equivocation that is defined as H of A given B, which is equal to probability of B j summation probability A I given B j log of 1 of A I B j. Now, since each of this term in the inner summation being of the form 1 multiplied by log 1, if this is equal to 1, or 0 multiplied by log 1 by 0, if this quantity is 0, what it implies that H of A given B will be equal to 0. Now, this conclusion is also evident in view of the generalization of Shannon's first theorem. The outputs of a noiseless channel are sufficient by themselves to specify the inputs to the channel. Hence, the average number of bits necessary to specify the inputs when we know the output is obviously 0, and therefore, I A B, which is equal to H A minus H of A given B, will be equal to H of A. So, the amount of information transmitted through such a noiseless channel is equal to the total uncertainty of the input alphabet. So, we get complete information of the. Now, let us look at the calculation of IAB for deterministic channel. Now, the example of deterministic channel is shown here. So, for deterministic channel, the input symbol A I is sufficient to determine the output symbol B j with probability 1. So, what it implies that all the probability B j given A I are all either 0 or 1. Therefore, for this case H of B given A, which is of the form summation P A I A B summation over B probability of B j given A I log of B j given A I. Now, since each of this is of form 0 or 1, what it implies again H of B given A is equal to 0, and for deterministic channel I get mutual information equal to H of B, that is the entropy of the output alphabet. Now, having looked at the definition of mutual information and some of the specific information channel, it would be interesting to see what happens when we cascade two information channel. So, let us look into some of the interesting properties of entropy and mutual information by considering the cascades of two channels. So, we will assume that we have two channels which have been cascaded as shown in this figure. I have channel 1 which is cascaded with channel 2 the input alphabet for the channel 1 is denoted by A and the size of this alphabet is R. The output alphabet of channel 1 is denoted by B and the size of which is S. Now, the input alphabet of the second channel is identified with the output alphabet of channel 1. So, the input alphabet for channel 2 would be equal to B and the output alphabet for channel 2 is denoted by C with the size of the alphabet being T. So, now from this figure it is clear that alphabets are connected by the cascades as shown in this figure. So, what it implies that certain relationship among the symbol probabilities will exist. So, let us look into those relationship. When AI, a symbol from A is transmitted along the channel 1, the output of the first channel is say B j. In turn, B j produce an output C k from the second channel. The symbol C k depends on the original input A I only through B j. What it means that if we know the intermediate symbol B j, the probability of obtaining the terminal symbol C k depends only upon B j and not upon the initial symbol A I which produced B j. So, this property of cascaded channels may be written as probability of C k given B j and A I is equal to probability of C k given B j for all I j k. In fact, this equation may be taken as a definition of what we mean by the cascade of two channels. Now, a direct application of Bayes' rule which we studied in the earlier class yields a similar equation in the reverse direction. So, we can show that probability of A I given B j C k is equal to probability of A I given B j. Let us try to prove this relationship. So, it is not very difficult to prove that probability of A I given B j C k can be written as by Bayes' rule probability of joint event A I B j C k divided by probability of B j C k provided probability of B j C k is not equal to 0. Now, this can be written as probability of C k given B j A I multiplied by probability of B j A I. Probability of B j and C k is probability of C k given B j multiplied by probability of B j. Now, this can be further simplified as probability of C k given B j A I. This is equal to probability of A I given Bj multiplied by probability of Bj. Now, probability of Ck given Bj is equal to probability of Ck given Bj Ai, because Ai, Bj, Ck's are the inputs and the outputs of the two cascaded channels. So, we have just seen the definition of cascaded channel is that probability of Ck given Bj Ai is equal to probability of Ck given Bj. So, this quantity is substituted by this, and we write this as probability Bj, and this terms cancel. So, what we get finally is probability Ai given Bj. So, we have shown that for a cascaded channel this condition is true. Now, it should be emphasized that probability of Ai given Bj Ck is equal to this, and probability of Ck given Bj Ai is equal to probability of Ck given Bj. These two relationships are only valid for the case where A, B, C are the alphabets of cascaded channels. Now, as we transmit information through cascaded channels from A to B to C, it is expected that the equivocation, that is H of A given C, should be greater than the equivocation H of A given B. Let us investigate this question. So, H of A given C minus H of A given B is equal to probability of A C log of 1 by probability A C minus probability of A B log of 1 by probability A given B. These summations are double summation over the alphabet A C. This is a double summation over alphabet A B. Now, for convenience, we will draw the subscript A I B J C K whenever we are summing over the symbols of the alphabet A, B and C. Now, this can be rewritten as probability of A, B, C over input alphabet A, B, C log of 1 by P A C minus A, B, C probability of A, B, C log of 1 by probability of A given B. This can be simplified as probability of A, B, C summed over the alphabets A, B, C log of P A given B divided by P A given C. Now, in this expression we use the relationship which we just derived, that is probability of A given B C is equal to probability of A given B. If we use this relationship in the last equation, then we can write as H of A given C minus H of A given B equal to probability of A B C log of probability A given B C divided by probability A C and we get the relationship finally as probability of A given C summed over A. Now, summation of probability A given B C over alphabet A and the summation of probability A given C over alphabet A both is equal to 1. So, for this term out here, we can use the earlier relationship which we had derived, that is x I log of y I x I summed over I equal to 1 to q is less than or equal to 0. So, using this relationship, this quantity out here is always greater than or equal to 0. So, what we get finally is H of A given C minus H of A given B is greater than or equal to 0, which implies that H of A given C is greater than or equal to H of A given B. This quantity can be written as H A minus I of A C greater than equal to H A minus I of A B. This implies that I of A B is always greater than or equal to I of A C. So, this shows that the information channels tend to leak information. What it implies that the information that finally comes out of a cascaded channels can be no greater than the information which would emerge from an intermediate point in the cascade if we could tap such a point. The condition for equality to hold in these equations is of some interest. So, retracing the steps in our proof to arrive at this equation, we see that the equality holds if and only if probability of A given B C is equal to probability of A given C. So, this is should be true for all A symbols and all B and C symbols such that probability of B C is not equal to 0. So, B C not equal to 0. Now, the condition for equality deserves some comment. At first glance, it might appear that equality would apply if and only if the second channel in the cascade is noiseless. Now, it is not very difficult to show that for a noiseless channel this condition is valid along with this condition. So, for a noiseless channel you can show that this condition is always valid, in which case you get the equality. But other than noiseless channel also it is possible that this equality is satisfied, in which case H of A given C would be equal to H of A given B, which in turn would imply that mutual information, that is I of A B, will be equal to mutual information I A C. So, let us look at one example which illustrates this point. So, let us take channel 1 with a channel matrix given by P1 equal to 1/3, 1/3, 1/3, 0, half, half. So, this channel has 2 inputs and 3 outputs, and this channel is cascaded with another channel which is indicated by channel 2 with the channel matrix given by P2 equal to 1, 0, 0, 0, 2/3, 1/3, 0, 1/3, 2/3. So, when we cascade channel 1 with channel 2, we can get the channel diagram for the cascaded channels as indicated here. So, for the channel 1, we have so, this is A1, A2, B1, B2, B3. This is 1/3 probability of B1 given A1, probability of B2 given A1 is also 1/3, and probability of B3 given A1 is also 1/3. Probability of B2 given A2 is equal to half, and probability of B3 given A2 is half. Now, this channel is cascaded with another channel. So, the channel diagram follows. This is C1, C2, C3, this is equal to 1. Probability of C2 given B2 is 2/3, this is 1/3, this is 1/3, and finally this is 2/3. So, this is the channel diagram for the cascaded channels. Now, for this channel, if we wish that IAC is equal to IAB, then the recently derived condition should be valid, and for this example what we are supposed to show is that probability of A1 given B1 is equal to probability of A1 given C1, probability of A1 given B2 is equal to probability of A1 given C2, probability of A1 given B3 is equal to probability of A1 given C3, probability of A1 given B2 is equal to probability of A1 given C3, probability of A1 given B3 is equal to probability of A1 given C2, and probability of A2 given B2 is equal to probability of A2 given C2, probability of A2 given B3 is equal to probability of A2 given C3, probability of A2 given B2 is equal to probability of A2 given C3, and finally probability of A2 given B3 is equal to probability of A2 given C2. So, if we want that the mutual information of the cascaded channel IAC should be equal to IAB, then all these conditional probabilities should be equal. We have taken all those cases for which probability BC is not equal to 0. Now, for this example, it is easy to show that this is true, in which case we get I of A B is equal to I A C. Now, to calculate probability of A given C, we would require to calculate the forward probabilities P of C given A and also probabilities C. Now, this can be easily done for this example, and it can be shown that the equivalent channel matrix between A and C is of the form so probability of C1 given A1 is this, probability of C2 given A1 is 1/3, probability of C3 given A1 is again 1/3, and probability of C1 given A2 is 0, probability of C2 given A2 is half, and probability of C3 given A2 is half. So, we can use this relationship, this equivalent channel matrix to find out the backward probabilities and probabilities of C, and we can show that this relationship is valid. Now, let us take an example of two binary symmetric channels and cascade them. So, let us assume that the binary symmetric channel is given with the channel matrix as follows. We take two identical binary symmetric channels and cascade as indicated here. Let us try to evaluate the mutual information between A and C and also between A and B. We will assume that the two possible inputs to the first binary symmetric channel are chosen with equal probability. So, we have seen that I of A B is equal to 1 minus H p, because if omega is equal to half, then H of omega p plus omega bar p bar is equal to 1, in which case we get this relationship. Now, if we cascade the two channels, then the equivalent channel matrix between A and C can be obtained, and it is not difficult to show that for the cascade of this two binary symmetric channel, it is equivalent to a single binary symmetric channel with probability of error as 2 p p bar. So, if we cascade, we will get the equivalent binary symmetric channel as follows. P squared plus p bar squared. So, this is the equivalent channel matrix between A and C. So, for this, based on a single binary symmetric channel results, we can find out I of A C is equal to 1 minus H of probability of error, in this case is 2 p p bar. Now, we can extend this result to 3 binary symmetric channels. So, if we take this and cascade it with another binary symmetric channel, where the output of the second binary channel, that is C, is fed to, and we get an output, final output is D. Now, for this case, we can obtain the equivalent binary symmetric channel between A and D by taking this matrix and multiplying by this matrix to get the final result, which is indicated here. P bar squared plus p squared plus 2 p squared p bar 3 p bar squared plus this quantity is repeated here and this quantity will be repeated here. So, for this equivalent channel matrix, the probability of error now is given by the term here. So, for this between A to D, we can find out the mutual information as 1 minus h of 3 p bar squared plus p cube. Now, if we plot the mutual information for all these 3 cases, we will get a result something of this form. This is IAB, this is IAC, and finally, we have IAD indicated here. So, on the x axis we have P, and on the y axis we have a mutual information. This is IAB, this is IAC, and finally, this is IAD. So, from this it is clear that for given probability of error P, IAD is less than IAB. In many types of information channels encountered in real life situation, the set of channel output is far larger than the user would like. So, the question is it possible to reduce the number of outputs by cascading the output of this channel with another channel where the output size of this new channel is less than the input alphabet size. And if you are able to achieve this, then is it possible to simplify the channel without paying a penalty in reduced mutual information? These questions we will examine in the next class.